Hey guys, part two of the video is going to happen at school, so if somebody walks in or there's an announcement, I'll try to pause it, but just bear with me. So let's get straight to it. So what we're going to be doing now, we've talked about how to create dot plots and histograms and all of those things. Now we're going to look at how we interpret them and how we look at key characteristics to describe what they are. So visual displays can be described by their shape. The first thing we're going to talk about is the spread of the distribution. This refers to the variability of the data. How spread apart is it? So we've already talked about how to calculate measures of variability like mean, absolute deviation, and range. Now we're going to look at, once it's on a visual display, how can we look at those things by just seeing it. So if the data cluster all around a single central value, then the spread is considered small. Numerically, this would mean you have a low range or a low mean absolute deviation. The further the observations fall from the center, the larger or the greater the spread of variability. So this would be a high mean absolute deviation or a high range or IQR. So here are some examples, just arbitrary examples of these are all kind of really close to their median here, whereas these are really spread apart and it's harder to see what that median would be. Here you can tell what the median is going to be, but still it's more spread out, so that's a larger spread. Okay, the next characteristic we're going to look at is skew. A distribution is considered skewed when it has more values on one side of that median, of that center, or the mean compared to the other. So we name them by their tail. I don't know why we do that, it's just the way we name them. So you can see this one has a tail kind of trailing off over here. We call this skewed left. Same thing with the dot plot. It kind of slopes upward over here. The tail is to the left, so it's skewed left. One thing we can know about a data set is, without calculating it, if you look at a data set and it is skewed left, so it's got a tail on the left, then the mean is going to probably be less than the median. Let's get a normal size pen here. The mean is going to be less than the median if it's skewed left. Left, less than. That's how I remember it. Skewed right is exactly the opposite. We're going to have histograms with a tail to the right where I've got huge, all right, this old trick, where we've got lots of data here and then it kind of trickles off to the right. Same thing here. I've got a tail over here and then it's sloped up this way. I bet you can predict if a distribution is skewed right, then we can assume that the mean is going to be greater than the median. Depending on its level of skewness, how much of a tail it has, the mean may be a lot greater than the median or just a little, but we can know that the mean is going to be at least somewhat bigger than the median. Now, if you've got a data set that looks nice and symmetric, that kind of looks like a parabola. Sometimes you'll see this referred to as a normal curve or a bell curve. This is a symmetric set of data. You've got your median here and you've got approximately the same number of data points falling above and below that, that middle peak there. In this case, we can assume that the mean and median are about the same. Okay, it's, you know, statistics has a lot of kind of drawing conclusions based on data, and it's never exactly, or it's rarely exact. We're making assumptions and we're drawing conclusions, and one of the conclusions we can draw from a symmetric data set is that the mean and the median are going to be close. If it's perfectly symmetric, they'll be exactly equal. If it's just kind of pretty much symmetric, like this one's not perfect, this one looks a little bit higher than this one, still mostly symmetric, so the mean's going to be pretty close to the median. Okay. All right. The next thing we're going to look at is peaks. This is drilling into what the mode is. So a distribution can have few peaks or a bunch of peaks. A peak is just an area of a distribution that has more data values than the other parts. So it's like you can see the mode visually. So we call it unimodal. Again, there's that root word of mode. If a distribution has just one peak. So these are examples of unimodal data sets with a histogram and a dot plot. We call it bimodal if there are two peaks. So you can see, and the peaks don't have to be equivalent. So when you look at this example, This is clearly your mode, right? It's higher than anything else, but I really do have two distinct peaks in this data. I've got two spots where a lot more happened than in the other places. Same thing over here with this dot plot, the duration of eruptions of a volcano. We've got a lot falling here right below 2 on the Richter scale, and then we've got a lot right here at 4.5. That's two distinct peaks where data occurs a lot. So we would call those bimodal. Also, sometimes you'll see ones that look like this. It's kind of rare, they're kind of crazy, but a distribution is considered uniform is what we call it when it's kind of across the board the same. So the data is sort of evenly spread across the range. And that would be a uniform data set. All right. That's pretty much it. I probably could have added this on to part 1 of the video, but that would have been 20 minutes. So there's not an application. It's kind of built into that interpreting. So a lot of the practice is going to be not just creating these dot plots and histograms and things, but also using them to draw conclusions and things like that. So if you're having trouble, let us know, but good luck.